So this is the solution to section 3 in chapter 4, which is titled Right Triangle Trigonometry. So let's start off with the first few problems here, and what they're asking us to do is find the exact values of the six trigonometric functions of the angle theta. Okay, so here's theta. Now it says explain why the function values are the same. Well, one is they're similar triangles. You can see the ratio of the sides is the same. 6/3 is 2/1. So, and they're both right triangles. So with that information, we know that they are similar, and hence the trig functions should be the same. So from a right triangle geometry standpoint, we have this information. We have that the sine of theta is the length of the opposite over the hypotenuse. The sine of the cosine of the angle is adjacent over hypotenuse. The tangent of theta is the opposite over the adjacent. The cosecant of theta is the hypotenuse over opposite. The secant of theta is hypotenuse over adjacent. And the cotangent is the adjacent over the opposite. So you can see how these are just reciprocals of each other. So if we can find the length of the third side here of either one of them, so the Pythagorean theorems, let's call this side x. So we'd say x squared plus 1 squared equals 3 squared. Squared plus that squared equals that squared. And so what does that leave? That'll be x squared is equal to 9 minus 1, which is 8. So x is the square root of 8. So this unknown side here is the square root of 8. And if you did this one, that would be the square root of, it would be 2 times the square root of 8. 2 times the square root of 8, because everything else is doubled. And you can see that's true if you take, let's say x squared plus 2 squared is equal to 6 squared. So you get x squared is equal to 36 minus 4. 6 squared minus 4 squared, that's 32. So x is equal to the square root of 32. But that is 4 square root of 4 times 8. But the square root of 4 is 2, so you get 2 times the square root of 8. Okay, so it works out. No big surprise there. Okay, so here we go. So this is for problem 1. The sine of theta is opposite. Let's use this one. Opposite over hypotenuse. The cosine of theta is adjacent over hypotenuse. The tangent of theta is opposite over adjacent. Now this one, because I have the square root of 8 in the denominator, I'm going to multiply and divide by the square root of 8. And so you'll end up with the square root of 8 divided by 8. Now, all these other trig functions, just the reciprocal. So you get the cosecant is 3. The secant of theta is 3 divided by the square root of 8, or 3 times the square root of 8 divided by 8. And then the tangent of the cotangent of theta is going to be 8 divided by the square root of 8 instead of the square root of 8 divided by 8. So you multiply by the square root of 8 in both the numerator and the denominator, and you get the cotangent, in this case, is going to be the square root of 8, because these become 8, and the 8 cancels out with that 8. We're just left with the square root of 8. Okay, the next thing is says sketch a right triangle corresponding to the trigonometric function of the acute angle, which means less than 90 degrees. Use the Pythagorean theorem to determine the third side and then find the other 5 other trigonometric functions. So in the previous problem, we were given 2 out of the 3 sides. We got the same kind of deal here, but they want us to create the right triangle. And we're going to define the angle to be here, theta. And this is going to be a 90-degree angle. So it says the sine of theta, which is opposite over hypotenuse, is 3/4. So we're going to make the opposite side 3, the hypotenuse 4. And then if we want to solve for x here, the third side, we've got x squared plus 3 squared equals 4 squared. X squared plus 9 is equal to 16. X squared equals 7. X equals the square root of 7. So that's the third side given this information. Okay, so now that we know that, we now have the triangle. So let's insert another page. So we know what the sine of theta is. That was what was given, 3/4. And what I'm going to do is I'm going to write over here adjacent. So we got the opposite is 3, the hypotenuse is 4, the adjacent was equal to, where is it here? Square root of 7. Okay. So the square root is the adjacent is the square root of 7. So okay. So the cosine of theta is the adjacent over the hypotenuse. The tangent of theta is the opposite over the adjacent. And again, multiply and divide by the square root of 7. So we get 3 times the square root of 7 divided by 7. The cosecant is 4/3. Take the reciprocal of those. Instead of adjacent over opposite over hypotenuse is hypotenuse over opposite. The secant of theta is going to be 4 divided by the square root of 7, which again will multiply and divide by the square root part, so you get 4 times the square root of 7 over 7. And then the cotangent of theta is, well, what we could do is just take this original part. We had simplified it to get rid of the square root in the denominator, but here we can just take the unsimplified version and then flip it, and then it's just exactly what we're looking for. So that's the cotangent of theta. Okay, next one. So we draw a triangle, and it's saying the cotangent. I'm just trying to draw this, so I think it's appropriate, or at least somewhat representative. So this is my angle theta. Here's my right angle. It says the cotangent is 5, which is 5 divided by 1. And the cotangent is the adjacent over the opposite. So I'm going to make this 5. I'm going to make this 1. And then the Pythagorean theorem will say this is the square root of 26. Why? 5 squared plus 1 squared, which is 25 plus 1 is 26. Take the square root, you get the third side. So here we have the adjacent side is 5, the opposite side is 1, the hypotenuse is the square root of 26. So now we're going to add a page and do our stuff. So you've got the sine of theta. That's opposite over hypotenuse. which is going to be equal to the square root of 26 divided by 26. We have the cosine of theta, which is adjacent over hypotenuse. So what we end up with here is 5 times the square root of 26 divided by 26. We have the tangent of theta. Well, one easy way is just to do the reciprocal of the cotangent. Then we go with the cosecant of theta. Again, let's go up here and see what it is. See, the unsimplified version was 1 over the square root of 26. So we're going to just say it's the square root of 26 over 1, which is the square root of 26. And the secant of theta is going to be 1 over the cosine of theta, or switch those two. So you end up with the square root of 26 over 5. And we already know the cotangent of theta is equal to 5 per definition of the problem. Okay, next one. Use the given function values and trigonometric identities, including the cofunction identities, to find the indicated trigonometric functions. So we're told that the sine of 30 degrees is 1/2. And is it tangent of theta or tangent of 30? Let's see if I've done this right here. Oh, yeah, it's a tangent of 30. So this is given. We could have found that from the unit circle. Okay, so let's do A. The cosecant of 30 degrees. So how could we find that? Well, because the reciprocal of the sine is the cosecant. So that would make that one's easy actually. So the cosecant of theta is 1 over the sine of theta, and the sine of theta is equal to 1/2. So 1 divided by 1/2 is 2. So that's A. B is the cotangent. So we have the tangent. The cotangent of theta is equal to 1 over the tangent of theta. So we get 1 divided by the square root of 3 over 3, which is equal to 3 divided by the square root of 3. So we take the reciprocal of the denominator and multiply it out. But then we're going to multiply and divide by the square root of 3. So we get 3 divided by 3. So we just end up with the square root of 3. So that's cotangent of theta. Now, the cosine of theta. So how do we do that one? Well, let's see. I'm just going to check to see what we know as far as identities. Okay, yeah, we do know the Pythagorean identity. So the Pythagorean identity says the sine squared of theta plus the cosine squared of theta equals 1. So what we have is this is the sine of theta squared. So we take the sine of theta squared plus the cosine of theta squared equals 1. And 1/2 squared is a quarter. 1 squared is 1, 2 squared is 4. Then we have the cosine of theta. Quantity squared is equal to 1. Subtract a fourth from both sides, so you get the cosine of theta squared is equal to 1 minus a fourth, which is 3/4. And then if you take the square root, you get the cosine of theta is equal to the square root of 3 divided by 2. So that's that one. Now, the last one, which is the cotangent of 30 degrees. Let's see if there's anything that says that we might be able to use there. Well, we have this one that says 1 plus the cotangent square of theta is equal to the cosecant squared of theta. So I know what the cosecant squared of theta is. I've done that in one of the problems already, which says the cosecant is 2. Cosecant of 30 degrees is 2. So I get 1 plus the cotangent of 30. I can put in 30. The cotangent of 30. And again, I'm going to rewrite this cotangent squared as cotangent quantity squared. This is just how the notation works. And then you have cosecant squared. So you get 2 squared. So we end up with the cotangent of 30 is equal to, squared is equal to 4 minus 1. 2 squared is 4. Subtract 1. So you get the cotangent of 30 is the square root of 3. So does that make sense? Well, actually, I could have done it without doing that. I could have also just said that the cotangent. Is that what they were asking me? Cotangent of. Oh, wait a second. What did I do here? I think I got some of these mixed up. Yeah, so I've done this twice. So the question is, how do you get the cotangent of 60? And again, I got to see what things you know, what things we're knowing relative to. Oh, yeah, here we go. So there's this other trig identity. So what we're doing is we're doing this one finally because I apparently didn't do it the first time. So let's go back to B. So it says, this is on page, well, you might have a different book than I do, but it says that the cotangent of 90 minus theta is equal to the tangent of theta. So in our case, the cotangent of 90 minus 30 is equal to the tangent of 30. And 90 minus 30 is 60. So the cotangent of 60 is equal to the tangent of 30 degrees. So I know what the tangent of 30 degrees is, so therefore I also know the cotangent of 60 is equal to the square root of 3 over 3. Okay. I think we got another one here. Must have one further down here on my page. No. So this is 4. Oh, here's 5. Okay. So we're given the cosine of alpha is 1/3. So what is first A? Secant of alpha. So secant of alpha is equal to 1 over the cosine of alpha. So that's one of the trig identities. It's called the reciprocal identity. So we get 1 over 1/3, which is 1 times 3 over 1. So we take this, multiply by the reciprocal. So we get 3. So that's the secant of alpha. Okay. B, what is the sine of alpha? So we could use the Pythagorean identity again, which I think is what we'd have to do. So you'd say the sine of alpha squared plus the cosine of alpha squared equals 1. So we get the sine of alpha squared plus 1/3 squared equals 1. Sine of alpha squared. So this is 1/9. So we're going to subtract. So this is 1/9. 1/3 squared is 1/9. 1 minus 1/9 is 8/9. So we get 8/9, and therefore the sine of alpha is equal to the square root of 8 divided by the square root of 9, which is, the square root of 9 is 3, and the square root of 8 is 2 times the square root of 2. How did I get that? 8 is 4 times 2, the square root of 4 is 2. So that's that one. The cotangent of alpha. So we've got the Pythagorean entity that relates the cotangent to the, well, actually we can use this one. It's the cotangent is the cosine over the sine. That's called the quotient identity. So the cosine is 1/3 from problem statement. The sine is 2 times the square root of 2 divided by 3. So we get 1/3, take the reciprocal, 3 divided by 2 times the square root of 2. So these cancel out. And then you can multiply and divide by the square root of 2. So you'll get 2 times the square root of 2 times the square root of 2. So that's 2 times 2, which is 4. And in the numerator you have the square root of 2. And then finally, the sine of 90 degrees minus alpha, according to the textbook, the sine of 90 minus alpha is equal to the cosine of alpha. So that's also equal to 1/3. Okay, evaluate the trigonometric function by memory or by constructing an appropriate triangle for the given special angle. Okay, so well, I know it from memory. So I'll explain how to do it the other way. So the sine of 45 is the square root of 2 over 2. B, cosine is square root of 2 over 2. And C is going to be 1 divided by the square root of 2 over 2, which is 2 divided by the square root of 2, which if you multiply the numerator and the denominator by the square root of 2, you'll get the square root of 2. So that's the cosecant, which is, it's also the secant because these have the same value. Okay, the other way of doing it is if you drew a 45-degree angle. So that's this. What happens, this also has to be 45 degrees. This has to be 90. So this is one of these 1, 1 square root of 2 triangles. How do we know that? Well, we know these are even because of the symmetric nature of these two angles. And if you take 1 squared plus 1 squared, you get 2. Take the square root, that'll give you the hypotenuse. So then you can just use the definition. You know, the sine of 45 is going to be the length of the opposite over the adjacent, and if you multiply and divide by the square root of 2, you'll get square root of 2 over 2. And the same thing for the cosine 45 degrees. You have the adjacent over the hypotenuse, which again can be converted to the square root of 2 over 2. And then the cosecant of 45, cosecant is hypotenuse over adjacent, so you get square root of 2 over 1, which is the square root of 2. Find the values. Okay, so what they're asking you to do is find the value of theta in degrees and radians without the aid of a calculator. And you know, we're in this section called right triangle trigonometry, so we should try to do this without using the right triangle. Remember we had two triangles that we've been dealing with that address the main angles that we saw in a unit circle. You have the you have this right triangle which has 30 and 60 degrees. So this is 60 degrees. This was the length of the hypotenuse was 1. This side, if we had this started out with the equilateral triangle, this whole side was 1, so this side is 1/2. And using the Pythagorean theorem, this is the square root of 3. So this is and this is 30 degrees. This is 90. So it's 30, 60, 90. And then the other triangle we had was the right triangle where the two sides are equal, and that gives us the 45 degrees. So this is 1, this is 1, so this is equal to the square root of 2. This is 90 degrees, this one is 45, and as a consequence this one also has to be 45. So we're going to use those two things to answer these questions, and we'll do it in terms of theta, and then we can convert them to radians just by using the conversion from degrees to radians. So number 7, sine of theta equals 1/2, and that is, the sine of theta is opposite over hypotenuse. So we go up here, and remember for the 45 degree, the angles, or the trig functions, were the square root of 2 over 2. So this doesn't involve the square root of 2 or 2, or the square root of 2 at all. So it's got to be this triangle. And you'll notice that if we want to get 1/2 as the result, opposite over hypotenuse, or opposite over hypotenuse, well, this one looks like is the value that we want to use, opposite over hypotenuse, and the angle that this side is opposite is 30 degrees. So the answer, so just looking at this particular triangle, we'd say theta equals 30 degrees. And then to find radians, you take theta in degrees, and you'd multiply by pi divided by 180. And so you would get pi over 6. That's, if you simplify 30 divided by 180, it gets 1 over 6. So that would be pi over 6 radians. Okay. So that is number 7a. So let's do 7b now. Cosecant. Cosecant of theta. Cosecant is 1 over the sine, and the sine is opposite over hypotenuse. So if you find the sine, and it says it's 2, so again, looking at these ratios of these different sides, you can see the only one that's going to give us 2 is the ratio of this side, hypotenuse, to this side. So to get 2, we'd have 1 over 1/2, and so the answer is the same as the previous part. So it's theta equals 30 degrees, because 30, this side have 1/2 is opposite. This is the opposite part in the definition, is the 30 degrees part. So again, it's 30 degrees or pi over 6 radians. Okay, so that's 7a and 7b. Then you got the tangent of theta equals the square root of 3. So remember, tangent is opposite over adjacent. So we again look at these two triangles, and we see that none of these combinations are going to involve the square root of 3. So it's got to be this triangle. And so the two options, we could take this divided by that, or this divided by that. Well, because we just have the square root of 3, what we need is the opposite side to be the square root of 3 over 2, and the adjacent side to be 1/2. So in this case, if this is the opposite side, then the opposite angle has to be 60 degrees. And the adjacent side is 1/2, so it still has to be 60 degrees. So theta equals 60 degrees. And then we can convert that to radians by multiplying by pi and divided by 180 degrees. 60 divided by 180 is the same as 1/3. So we get pi over 3 radians. So that's the answer for 8A. And then for 8B, again, this does not involve the square root of 2. So it's not the 45-degree triangle. So we say the cosine of theta is the adjacent over the hypotenuse. So the only way we can get 1/2 out of these 3 side lengths is to have 1/2 in the numerator and 1 in the denominator. You know, if we did this divided by that, we'd get the square root of 3. If we did this divided by that, we'd get something involving the square root of 3. So the only one that doesn't involve the square root of 3 is the ratio of these 2 sides. And so the and the configuration where this is the adjacent side, the adjacent angle to this side is not the 90 degree, but is the 60 degree. So again, just reasoning through the triangle, we'd get theta equals 60, and we just did it previously. This is the same as pi over 3 radians. Okay, next one says use trigonometric identities to transform the left-hand side of the equation into the right-hand side. Now we're going to talk more about trig identities in chapter 5. But what we can do here is you can use, again, we are in the right triangle section. So what we can do is we can define these in terms of opposite adjacent hypotenuse. So cosine of theta is the length of the adjacent side over the length of the hypotenuse. The secant of theta is equal to the hypotenuse over the adjacent. So if you take the cosine of theta times the secant of theta, that's adjacent over hypotenuse times hypotenuse over adjacent, which is 1. See those? All these simplify down to 1. Now another way of doing this from previous sections would be to use the fact that the secant is 1 over the cosine. And I guess you probably use the same reasoning here as well. Okay, the next one, 1 plus cosine of theta, 1 minus cosine of theta equals the sine squared of theta. So what we do is we'd use FOIL here, and so you'd see the inner and outer cancel out because you got minus cosine theta plus cosine theta. So you get 1 minus cosine squared theta equals sine squared theta. Now from a yeah, it actually says use trigonometric identity. So this is probably the appropriate one, but you see it works using lengths of sides as well. So I'm going to do it both ways just to show you how these things come about. So let's just using lengths. So the cosine is the adjacent over the hypotenuse, and you square that, and that should be equal to opposite over hypotenuse squared. Now if we transform the left-hand side to find a common denominator, we'd have hypotenuse squared over hypotenuse squared minus adjacent squared over hypotenuse squared. Just leave that there. So you get hypotenuse squared minus adjacent squared over hypotenuse squared equals opposite squared over hypotenuse squared. Now what happens? What you do here is use the Pythagorean theorem. So the Pythagorean theorem says hypotenuse squared equals opposite squared plus adjacent squared. So hypotenuse squared minus adjacent squared equals opposite squared. Okay, so that's how you do it using the lengths of the different sides. But the trig identity that we'd use is the Pythagorean identity. And the Pythagorean identity says sine squared plus theta plus cosine squared of theta equals 1. So if I solve this for the cosine of theta, it's 1 minus sine squared theta. So I just subtract sine squared from both sides, and then I could substitute that in. So for cosine squared, I'll put in 1 minus sine squared theta. Now you got to be careful. Notice I put the parentheses here because I want to make sure this negative gets multiplied by both terms. So you get 1 minus 1 plus sine squared theta. And those go to 0. So the left-hand side becomes sine squared theta. The right-hand side is sine squared theta. And once you get to a point where they're equal to each other, then you can do that. Okay. And then number 11, again, we'll use the same substitution. So what I'm going to do is I'm just going to manipulate the left-hand side. And for the cosine squared of theta, I can put in 1 minus sine squared theta. So I've already kind of derived that. So you have 1 minus, for cosine squared, we'll have 1 minus sine squared theta. And again, you make sure you distribute that negative sign to both parts. So this negative times a negative becomes a positive. And then you combine these two, so you get 2 sine squared theta minus 1 equals something. Well, and now I can say, well, that's exactly what the original equation said. And because we can prove that's true, then that's we transform the left-hand side equation into the right-hand side of the equation. Okay, the next 2 problems are word problems. And this is showing you how you would figure out how high a mountain is by measuring the angle between the horizon or horizontal and the peak of a mountain at 2 points. And you would measure the distance between the 2 places you took the angle. Now, I don't need to know what the distance is from these points to the mountain, the center of the mountain. All I have to do is measure the distance that I'm traveling. So what we end up with is we end up with 2 right triangles. So we got this one right triangle like this, and the key thing is that the opposite side is the same for both triangles, and that's what we're trying to figure out. What is the height? So this is opposite. Okay, this is 3.5 degrees, this is 9 degrees, and this distance here is 12 miles. So we're going to figure out the height in miles. Didn't say, and actually that says 13, doesn't it? Not 12, it's just 13 miles. So there's actually 2 unknowns here. There's also this distance, which we are going to figure out. We'll just call that x. So here's our this right triangle here, the adjacent side is 13 plus x. So what we do is we say the tangent of 3.5 degrees is equal to the opposite over the adjacent. And then you take the second triangle, the tangent of 9 degrees is equal to the opposite over the adjacent. Now we have to use, you'll have to use your calculator to figure what these are in terms of the tangents. There's no shortcut like that. So, my calculator. Make sure your calculator's in degrees. So hopefully you've pulled it out. Okay. Yep, it's in degrees. Okay. So the tangent of 3.5 degrees, tangent of 3.5 is 0.06116 equals opposite over 13 plus x. And then we have the tangent of 9 degrees, which is 0.1584. That's opposite over x. And what we're going to have is two equations and two unknowns, but we can use substitution. So if we multiply both sides of this equation by x, you'll get 0.1584 x equals the opposite length. And then we can substitute into the first equation, so you'd have 0.0616 equals, we could solve for O and then X, or X and then O. I guess the way I've started here, I'm going to solve for X and then O, which is the height. Okay, so let's, for O, I'm going to put in 0.1584x divided by 13 plus x. And then you can multiply both sides of the equation by 13 plus x. That'll get rid of that in the denominator. Multiply that out. So 13 times 0.06116 is 0.75795. Take these out to 4 decimal points. 7951 plus 0.06116x is equal to 0.1584. As I said, go to 4 decimal points. X, and then you subtract 0.06116 from that. So 0.1584 minus 0.06116 is 0.09724x. And then we divide both sides by 0.09724 to solve for x. 7951 divided by 0.09724. X is 8.177 miles, and O is equal to 0.1. I'm going back here. 0.584x. So that's 0.154. That's x. That's m is for miles. So we get O is equal to 1.295 miles, and there are 5,280 feet per mile. 6,839 feet. Okay, so we're multiplied by 552.80 feet per mile. 6,839 feet. Now let's just go back and check to make sure this works. So we can go back here and just check out these numbers. So what we said was the opposite side, which is the height, was equal to 1.295 miles. X was equal to 8.177 miles. So if we find the tangent, if we take 1.295 divided by 13 plus 8.177, 295 divided by 13 plus 8.177, we get 0.0611. Yeah, we get that number. 0.0611. I get 5, just because of rounding off, I get that right. And then the second part, the 9 degrees, all you have to do is take 1.295 divided by 8.177, 295 divided by 0.177, 0.1584, 0.1584. So both those check out. Okay. And the last problem here, what we have is a tapered shaft. So a shaft is just it could be a solid shaft or a hollow shaft. In this case, it's a hollow shaft. The outside dimension, which we're going to call D, the diameter, is bigger on this end than this end. What you might use that for is sometimes to attach two pieces of metal together. You have a hole drilled, and then you put a tapered pin or shaft in there, and the taper kind of wedges things in there. So that's one reason you might do something like that. Okay, find the diameter of the large end given you have the diameter of the small end. So what you can see is that what we're going to do is we're going to create a right triangle here, and this dimension is, so if I extend this just straight without the taper, this dimension here is going to be 5 centimeters. And then this height with this right triangle that I'm going to make just by the taper part. So what you're going to have is something that looks like this, and this is 3 degrees, and this dimension is 15 centimeters. And what we're trying to do is figure out what is the opposite side. That'll be this distance right here, and then so the D will be equal to 5 centimeters plus 2 times the length of the opposite side for this triangle that's created by this outside part. So opposite over adjacent. So it says the tangent of 3 degrees is the length of the opposite side, which is what we're trying to find, divided by the adjacent, which is 15 centimeters. So the opposite side on this triangle is going to be 15 centimeters times the tangent of 3 degrees. So we'll plug that into our calculator, making sure that we're in degrees. 15 times the tangent of 3 degrees, which is the opposite side length is 0.7861 centimeters. And therefore, the final diameter on the large end of the shaft is going to be the diameter on the small end of the shaft plus 2 times this length that we calculated for our triangle. So 5 plus 2 times 0.7861. So we get 6.572 centimeters. And everything's in centimeters, so we can just do that. Yeah, taper 3 degrees is pretty big. You can see how much bigger the one side is. Okay, so that's it.